Yeah, and much less people and smaller groups and yeah. So I pasted the in the chat a link to OpenAlex. It's it could be one of the databases that you could use because, for example, I know some people used to scrape Google Scholar, but it has to be done cumbersome because they detect your IP, and if they notice that you are downloading lots of data, they will block your IP. So you need to shift your IP constantly.
I'd rather have that not happen to me.
Okay. Yeah, but okay, with this new database, it seems that there isn't that problem. But then let me.
Okay, I'll look into it. And even if I don't have enough data, I was wondering if it's possible to
say some salespeople that you get basically paid only if you make sales.
Yeah.
And I don't know whether there would be a balance in the sense that these two are extremes and they all have advantages but disadvantages, and maybe something in between might be more suitable in the sense that you have some security and you are not worried like, oh, I didn't make enough sales. Or the another example is the bus drivers, like in the microbuses, they're called hombres camión, because basically what you earn that day is what you, well, minus fuel, and if you're renting the unit, and the plaques if you're a taxi. So for example, some taxi drivers, they need to drive, I don't know, for example, airport cabs, they need to make like 5 or 6 trips, and only after they start earning for themselves. So the first they need to cover the plaques that they're renting, and the unit that they're renting, and the fuel that they're using, and then for them. So if they cannot,
and that's why bus drivers rush on the highway.
Yes, yes, but actually, when there used to be Ruta 100, let's say the public buses of Mexico City, at some point they were paying them by rounds, so they would not not even stop because let's say to make more rounds. It's like, well, what kind of service you're giving if you don't let people out or in? So then they told, okay, no, we will give them fixed salaries, but then they would be like, I don't know, 10 kilometers an hour or something like that, and stopping to chat, and because now they don't have motivation to to drive fast. And yeah, I mean, you can see with more modern bus drivers that they have shifted several routes to companies, because if a single driver in this model where you basically earn day by day, if you fall ill, then you don't earn money. You don't have holidays, and you don't have insurance, and no retirement plan, no anything. So several lines they kind of organized into companies. I mean, because they're not cooperatives. It's like some people invest and buy the units, and then they hire the drivers. But then these drivers, they have a fixed salary, and the Metrobus drivers are also like that. They have a fixed salary, some sort of insurance, some sort of capacitación, training, yeah, vacation, I guess. So many drivers say that is much better, but also because they're earning as much or even more than what they were earning before. So it's not only which mode, but whether you can earn more or less with which mode, because let's say if you earn the same, then everyone would prefer, let's say, the safe, calm option that you don't have to worry whether you will make it or not. But then if like that, you make much less than what you would with more stress, then some people might choose to be stressed but earn more. Yeah. And it also depends on how much, no? Because, and for example, the metro drivers, they have a union and they have a fixed salary, but then they get paid extra for extra hours. So they make programs. So in order to know when a driver will start working, so some will start at 5, and then some others at 5:30, some others at 6, some others at 6:30, and so on. And then they have like also their breaks, and how other drivers will take the trains at which moment and things like that. But the schedules are made in such a way that every day every driver will work 1 or 2 extra hours, and they get paid for those. So that's a kind of bonus, but it's a negative incentive, because you are if they get delayed, they are better off. So how do you know that they're not doing it on purpose? and the whole system is delayed because they want to earn a bit more. All this is part of a much broader topic of incentives, no? How to motivate people.
Yeah. Thank you. Thanks for the insight.
Okay, interesting. So yeah, try to play a bit with simulation and see what comes up.
Okay, thanks.
Who will be next?
I haven't shared my project.
Yes, please go ahead, Daniel.
Well, I have two ideas. The first one would be to work on my thesis subject, and that would be, I'm trying to work on random walks with multiple walkers that have stochastic resetting to a point in the network, and the idea is to work here the part of the multiple walkers, and that's one idea. But I don't know if it has to do too much with the topics we've seen in the course. What I would do, and I have another idea. Oh yeah.
We haven't seen much of networks, but we will. So
okay.
it is related. But yep, please go ahead.
Yeah, I have another idea. That's how do you? It has to do with music and musical preference of genres in music, and how do you obtain such a preference for a type of genre? And the idea is to model something like a forest fire model or something like that, and give value to the I don't know, the context that each genre arises in, and the type of sounds it has, and the complexity of the structure of the music, and I don't know, you can change your opinion or change or absorb or like one type of music if it kind of goes with the it's not that high complexity, or it kind of goes with your context and how that changed. And I was thinking of that because of how music is so international right now. But if you show like reggaeton to some person that only listens to classical music, they don't adapt it. But if you show same reggaeton to something that to some person that likes I don't know, bachata, no, I don't know anything. They probably will like it more.
You're entering a dangerous territory.
Yeah, it's not a question of which is better or worse. It's just a question of what makes you like each kind of music. Does it have to do with the complexity or the type of rhythms or the structure?
Yeah. So, do you know where could you get data to test different hypotheses?
No, I saw a paper on +1 that makes a similar question, but it's just about complexity and on music, and how the preference of lower complexity music over higher complexity, and the instruments used, and how people tend to prefer some instruments than others. But that's just the only thing I found.
Because if you get data from some streaming services like Spotify or Pandora or something, in principle, I mean, it's of course might be too many assumptions, but let's assume that you can identify different genres, and then you kind of cluster them to see which users like, let's say, what you could make, let's say, a network of genre, and then you connect them with stronger weights if the same user listens with a certain threshold music from two different genres. And like that, you build a network, and then you seek correlations between that network and things like the entropy or complexity or some other thing. And then you could put those genres in a historical timeline, try to see whether those genres with similar correlation, whether one led to the other, meaning that, first of all, whether it's conclusive that anything tells you that, okay, these two genres, or people who like these two genres, they share some common property. and then to distinguish whether there would be some temporality in this, in the sense that if one genre first arose and then some people were listening to it, and then those people, or a subset of those people, kind of start liking another type of music, which was more recent.
Yeah. I think the only thing with the streaming services is it's a very narrow window of time for music, right? And it's more used by young people. Well,
I don't think that's a problem, because we keep on listening to music from all times.
Yeah, that's right.
So just even if you get data from last month, people still listen to say music from the 50s or earlier.
Yeah.
Let me. Yeah. Some colleagues from the Veracruzana recently published this. So they got their data somehow. So the second author, Carlos Piña, was a postdoc with me. So you can ask him and just write him an email with carbon copy to me and ask, how do you get that paper? Maybe it's described in the paper how they got it, because sometimes there's an API, and then like you can get Twitter data. I don't know whether you can get Spotify data in a similar way.
I think they just use the Mexico's top 50 in there's playlist. Yes. I don't know if it has to do.
Yeah, maybe they just did it manually.
Yeah.
But
yeah, Spotify each year has the top of Mexico and the top songs of the world and that stuff.
Yeah. Yeah. Then there's an older service called Last.fm. I don't know whether it's still active. But this is not so much a streaming service, but people would, you will have like a plugin or something in your computer, and then it basically logs which music you listen to. And then it would suggest you similar music and things like that. And this was before streaming services. I don't know whether it would be easier to get their data, because since this used to be web-based, meaning that you can see each user has a public web page. And then you can see what they're listening to and who are they following. So it's also like a social network. Then you can see, let's say, start building some network from that. Maybe that would be possible.
Okay. Thanks.
And maybe there are other steps.
Yeah. So do you think that could work with Last.fm and Spotify? I don't know. Maybe I have to concrete the idea a little bit more. But thanks.
Yeah. And about your thesis, these random walks with multiple walkers. What is the idea of having multiple walkers instead of just running simulations of lots of walks, but let's say in
The idea
series,
would,
not in parallel.
yeah, the idea would be to find the encounter times in the
Okay.
mean encounter times of the random walkers. There's a paper from my thesis advisor, the Alejandro Perez Riascos.
Yep.
And the idea is to try to replicate that, the simulations in the paper and all the math to then implement it on my own work with but with stochastical resetting of the multiple random walkers.
Yeah, I suppose you vary the network topology and then you see what differences that gives. Yeah.
Yes.
Something that might be interesting to explore in that setting would be also the heterogeneity of the walkers, in the sense that I can imagine that all your walkers move at the same speed.
Yeah.
And then you could make a variation. Okay, what happens if we have this distribution of speeds?
Oh, okay.
And this can be made in different ways. If all the weights in the network are the same, then the speed would be how many nodes you will traverse, or how often you will walk. Like you have, let's say, time steps, and some walkers will move every time steps, and others every 3 time steps, and every 10 time steps. Then you have a distribution, and then you change the distribution of speeds and see what would be the effect of that heterogeneity.
Yeah, that's a good idea. Yeah, I don't know which one to choose though, but both are great ideas.
Yeah, well, try to explore data options for the seconds, and if it becomes too cumbersome, then
then I go back to
that will make an easier choice.
Yeah. Okay. Thank you.
Okay. Someone else?
Me, Valeria.
Yes, Valeria.
Can I say it in Spanish? I feel more comfortable.
Yes.
Ok. Pues yo quería seguir como lo que iba a ser de mi tesis, lo que le había comentado de los autos autónomos. Pero tenía 2 ideas de lo de extender el paper de Distributed Management of Traffic Intersections, que era poner un auto que tuviera una prioridad mayor y que pues entre todos los autos se coordinaran para que pasara, pero ahí siento que se tendría que tener más carriles. Entonces no sé si es como más viable, porque el tener varios carriles puede que la cooperación se destruya y pues se haga todo un caos. Entonces otra idea era como que explorar todo el espacio de las reglas que se pueden tener si aumentamos solamente un carril más. O sea, aquí teníamos un carril, por ejemplo, de ir de sur a norte y de este a oeste. Pues nada más aumentar un carril que fuera de oeste a este, sin permitir como vueltas a la derecha ni vueltas a la izquierda, para ver cómo es que se están comportando y ya después, pues, a poner otro carril que vaya como de norte a sur.
Sí, pues con Jorge Zapotecatl, pues estaba trabajando lentamente en un artículo donde pues mejora las estrategias de coordinación en las intersecciones de autos autónomos, porque resulta que puedes tener múltiples estrategias, pero resulta que varían con la densidad, pero también varían con la topología de la red, en el sentido de que unos colegas de MIT publicaron hace años pues un algoritmo que parecía muy bueno para coordinar autos autónomos en intersecciones, pero todo lo hicieron para intersecciones aisladas y después asumieron, pues si tienen muchas, simplemente extiendes lo mismo y funciona, ¿no? Y pues con Jorge simuló eso y no funciona. Eh, digamos, cuando ya le empiezas a rascar, pues ves que empiezan a surgir correlaciones y pues sí, no es eficiente cuando lo quieres aplicar para una red de intersecciones. Entonces, pues lo mismo aplica para estas situaciones, aunque sean simplificadas. Entonces le puedes poner más o menos eh, elementos y pues eso te va a cambiar así como que cuál es la mejor estrategia.
Ok, y por ejemplo lo del...
Entonces,
perdón.
sí, entonces, digamos, no quiere decir que no haya que hacer exploraciones teóricas, pero como que en este tipo de problemas limitadas de lo normal.
Y por
Digo,
ejemplo...
porque,
No, perdón, otra vez.
sí, que en una ciudad real, pues no vas a restringir las vueltas y tal vez eso sí importe. Eh, pero pues bueno, conviene empezar por la versión más simple de todos modos.
Es que justo lo pensé porque pues el proyecto es como de 3 meses, o sea, y ya a lo mejor
Sí,
para toda la tesis ya permitir lo que son las vueltas, o sea, porque yo también pensé y dije, no, pues no es óptimo, pero para 3 meses solamente ver como las reglas, pues dije, no, pues sí es como más, real lograr hacerlo en 3 meses que ya con todo. Y por ejemplo, lo de la prioridad, lo de que un auto tenga mayor prioridad, no sé, igual también esa era mi otra opción, pero sí sería como, pues, por ejemplo, aquí en el paper tienen diferentes roles, ¿no? Lo que es el follower y ¿cómo se llama el otro? El,
Negotiator.
Ajá, justo, pues que ahora tuviera otro tipo de rol y que ya no se, bueno, eso sería cuestión de verlo ya en la simulación, que ya no se descontrolara todo porque va a ser un rol de que, no sé, el que tenga una emergencia, no sé, con cualquier nombre, este, ya dejarlo pasar teniendo ya los carriles, o sea, sin que como que todos pierdan y que se haga un caos.
Sí, sí, digo, es interesante porque también como que le podrías poner un nivel de preferencia y entonces, digamos, es un poco un tráfico por demanda, ¿no? Más o menos así funciona. Entonces a un vehículo le das la misma demanda que 2 vehículos o que 3 vehículos o que 10 vehículos y entonces es interesante jugar con ese parámetro para ver qué tanta preferencia recibe el vehículo y qué tanto te afecta el tráfico de todos los demás.
Mm.
Porque, por ejemplo, uno podría decir, bueno, si viene una ambulancia, una patrulla, pues todos se paran y pasa la patrulla, ¿no? Y pues que se paren lo que tengan que parar, pero en la simulación podrías medir precisamente a distintas densidades qué tanto te afecta. Y luego, por ejemplo, si es transporte público, pues quieres darle preferencia, pero tampoco quieres causar un caos vial nada más para que pase un camión. Entonces, como que ir buscando un balance entre qué tanta preferencia le das a cierto tipo de vehículos y qué tanto perjudican a otros vehículos, ¿no? Entonces, podrías comparar los escenarios donde nadie tiene preferencia y después empiezas a aumentar la preferencia y ves qué ventaja obtiene el vehículo que le dice la preferencia y qué tanto pierden todos los demás. Y entonces tratar de encontrar ahí un balance óptimo, que no sé si qué tan dinámico sea en el sentido de si depende de la densidad o de alguna otra cosa en el que pues le puedas dar lo máximo a los vehículos con preferencia y quitarle lo menos posible a todos los demás. Que, pues digamos, mientras menor es la densidad es más fácil. Bueno, también si la densidad es muy alta es muy fácil porque pues, todos están parados y pues nada más que le den preferencia al de a un vehículo y eso pues, no afecta mucho a los demás porque todo el mundo va a estar en el tráfico. Pero sí, sería interesante explorarlo eso de manera sistemática y entonces poder decir, pues lo mejor es una preferencia, no sé, 3.4, algo así.
Ok.
Sí, pero pues en ese sentido, pues hasta podrías empezar con un escenario muy, digamos así, de 2 calles, una intersección y luego ir extendiéndolo y ver si los mismos resultados se aplican cuando tienes más intersecciones o calles alternadas o variadas las fronteras, cosas así.
Vale, está bien.
Okay. Well, was there someone else? Okay, otherwise then let's move on to the Ashby paper. So this was of which year was this paper? 1947. So let's say right after the Second World War, cybernetics book I think had just been published. So it was like this paper was one of the first ones within the movement of cybernetics, which was strong throughout the 50s and 60s, and perhaps even beginning of the 70s. And it makes this analogy of the nervous system and how to study the nervous system in terms of physical machines. And the I mean, something interesting about nervous systems is that I mean, some first studies were made just 100 years before, middle of the 19th century. First descriptions of neurons were made by Ramón y Cajal around the turn of the 20th century. And I mean, by 1947, there had been already important advances, but one could say that not much was known about how our brain worked. I mean, it was still a phase where people were kind of classifying different structures, different types of neurons, but let's say their mechanisms were still not well understood because we didn't have the proper tools to measure, let's say, neural activity and to detect much details about their time scales and their connectivity. We are still very limited in how to study nervous systems. But of course, much has been advanced since then. So an interesting thing is that the ideas that Ashby poses here are not restricted to study of nervous systems, but they can be applied to machines. Or basically, he takes the abstract idea of machines and applies it to nervous systems, but we can take the same idea of machines and apply it to almost any phenomenon we perceive in any dynamical system. And philosophically, well, it's just interesting to know that it seems Ashby is a monist, in the sense, contrary to Descartes, that he doesn't assume that animals are machines, but the human is something different because it has mind or soul or whatever, and therefore we cannot study or relate mind with matter. And they're like two different things. Res extensa is matter, res cogitans mind. And Ashby takes the perspective that no, let's say, let's study mind from a physical perspective. And this opens up several important perspectives. One is that you are able to study mind by studying, let's say, a physical system. Also that you can build a mind. with a physical system. So let's say artificial intelligence as such was coined in 1956. People were already speaking about creating something that later would be called artificial intelligence. I mean, Alan Turing published his paper on whether machines can think in 1950. But let's say Ashby would be from the camp saying that, yes, we can build artificial intelligence because mind is something that can be formalized. And therefore, a machine could reproduce the same function that our minds have. There's not much mystical about it. But I mean, this like a bit of the preamble. I would be more interested in listening what you found interesting, or boring, or wrong, or what caught your attention. Yes, Amaury.
Well, when I was reading this paper, I put a lot of attention when Ashby looked for examples for what he called breaks in the nervous system. He didn't mention examples, but I thought about it. Well, for example, I could imagine a lot of this break phenomena when an embryo is being developed. These breaks can be visualized as genetic shifts that produce allocation among the primordial cells in the nervous system. Also, when we learn something, we exploit the plasticity of neurons with the aim of building new memories and gaining experience. So this is another kind of break. And also, when we pass from a resting state to an active state, many parts of the brain change its dynamics. Sometimes we find chaotic states, other we find periodicity, for example, in sleep. So this phase transition amidst different families of neurons can, of course, be thought as one of these breaks that Ashby mentioned. It's an interesting perspective, but obviously, well, now there are a lot of new research lines. For example, the integration theory of information, or the network space theory of information, and it's very peculiar, this approach of Ashby.
Yeah. And anybody else, or I mean, I can pose a question. What do you think about Ashby's notion of adaptation? Or whether you would like to comment on some other aspect. I think it's interesting to see, because much of the vocabulary that we now use didn't exist or was still information. So he tries to express some concepts that now have become better defined, and he kind of uses words that now, let's say, are not used in that context. But the ideas are the same. So it's interesting that, let's say, how the discourse, even when using different words, transmits more or less the same message. Or what would be an example of a braking system? Or a system that is difficult to break, in this sense.
Well, at the end of the text, Ashby made emphasis on how the environment and the individual are tremendously correlated, generating feedback loops. Well, he didn't use this word, right? But generating feedback loops between one and the other, between the individual and the environment. And obviously, this is very similar to the Gaia hypothesis proposed, I think, 30 years later than the Ashby's article, I think. And in this hypothesis, life can guide the dynamics of the habitat and vice versa. Of course, this can be extended because, for example, in social systems, we can consider and as environment not only the natural stuff, but the cultural background as well as the economical and political context of the individual. It's interesting to see this relation between the individual and the environment in general.
Yeah, that when speaking about very abstract things, like in this case, machines, it's a bit tricky because on the one hand, it applies to many phenomena, in some cases to most phenomena. But then if it's so general, then how much can you say about those phenomena that it's still meaningful? Because you could say like, I come up with universal law of everything, and it's simply stuff is. And well, yeah, it's valid, but it doesn't tell you much about anything. So it's interesting that in many cases, the ideas or the theories that were proposed within cybernetics and system theory were not so much, let's say, laws in the sense that physicists have proposed law of universal gravitation or thermodynamics or electromagnetism or things like that, but there are simply perspectives for describing phenomena. And then the question is whether these are useful or not. And in some cases they are, and in some cases they aren't. So, you could also say about physics that the laws are also descriptions of phenomena that might be useful in some contexts and in some others aren't so useful. But since they try to be as objective as possible and try to get rid of the observer, they have the illusion that they are independent of the observer. But actually they aren't. That's precisely the problem, which is not a problem with Newton's laws, is that of universal gravitation, that if you go to very high scales or very low scales, they stop applying. But it's not that they're wrong. It means that they're limited. But the same you could say of everything. For example, the second law of thermodynamics, it's not that, let's say, it's always valid. Well, you could say that it's valid because it's both in a precise sense, meaning that it's for closed systems, but most systems are open. So it's not that the second law of thermodynamics is violated. It means that we are facing every now and then most real-time situations are such that you can have energy coming in and therefore entropy decreasing with self-organization, for example, or other mechanisms. But we still have this notion that we will find true laws, but in a sense, they are just descriptions that are useful. And the ones from physics are very useful, but that doesn't mean that they are independent of the observer.
Yeah, I understand the point. A month ago, a group of scientists, guided by Banturing, I think, published a pair of papers in PNAS concerning to propose a theory of life. Its origin and evolution, based on learning theory. In fact, I think I shared in the chat of the class one of those papers. And this conception that Ashby uses when he talked about the breaks that a system can suffer as achieve the equilibrium is pretty consistent with the Van Turing perspective, because this is equivalent to minimize repeatedly a loss function, an essential abstraction in learning theory, before reach a total equilibrium in all its variables. So maybe the ideas of Ashby are not outdated. Maybe he just needs a new language, new vocabulary in order to improve their ideas. So yeah, I think language is very important for science. Maybe there are things that now we don't know how to express or how to define, but in the future, well, we can succeed in that.
Yeah. I mean, also, this was published 75 years ago. So it's not that it will still be completely valid, because so many things have advanced and changed since then. But I mean, this idea of machines breaking, I think it's similar to the notion that we are using in this course about non-stationary problems. Meaning that in a stationary problem, it means that you have the equations or some formal description of a system, and then nothing changes. But then when the machine breaks, it means that it changes. So it's like equivalent to having a different fitness landscape, and then you need to adapt. And this is also related to what we were speaking recently about the difference between finite games and infinite games, in the sense that in finite games, the rules are well defined and they don't change, or at least they change in predictable ways. Let's say there are rules that will tell you how things will change, which also applies to the ideas of Ashby. I mean, you can have, for example, systems with variables that will change in times, but it's not that they're breaking if you have the description of how those variables will change in time within the system. If those changes are not predictable, they come from outside the system, then you say that the system breaks and then it changes. But yeah, if you include those changes as part of the system, then the system doesn't break, and then you have a greater system that contains those changes. And it's the same with stationary problems. You can have a non-stationary problem because there's something that modifies the rules of the game. So, for example, temperature. If rules of the game change with temperature, like for example, sex in reptiles, if it's I forget which one is which, but below certain temperature, you'll get males, and above that temperature, you will get females. But then if you include that rule that depending on the temperature, you'll have different behavior or different function, then the system doesn't break because you're including it. So it's the same if complexity implies interactions that generate novel information, but you include those interactions in your model, and basically your machine is not breaking and you are containing all those changes. However, we can be sure that in many cases, there will always be changes that will break the machine, meaning that it's more, it's a better strategy or a better idea to try to build the system in such a way that it will withstand those breaks. Or to use a phrase from the 90s in the new wave of artificial intelligence known as behavior-based systems, we would like our machines to degrade gracefully. Meaning that if something changes, you want the machine still to continue functioning perhaps not as good, but not to break down completely. And there are ways in which we can build our systems so that they don't break down completely. So even if you have this break, meaning that there's a change in behavior, the function will not be terribly altered. And precisely this is the idea of robustness or resilience. And yeah, to combine adaptation and robustness and anti-fragility to achieve all of this. But these ideas that might seem novel, I mean, they're already here 75 years ago. And then the question is, well, if they are there already for 75 years, why haven't we introduced them in, I mean, not in everyday life, but let's say in university curricula or even research? I mean, many experts still don't take into consideration this type of changes or required adaptation. So why do you think this is the case that after? Because some people say that after, I forget the precise phrase, but it's something like, for a new paradigm to take hold, you need the old generation to die out. And it's been already several generations and it still hasn't died out. So why do you think this is the case?
In my opinion, it has more to do with the way we research. Because, well, I'll put an example. My mom, she's a biologist and she's an ecologist. And then, well, in her lab, they do a lot of research on temperate forests, and well, they research the interactions between individuals and different species and so on and so. But there has been a bit of push into including ethnobiology into ecology, but it's had a lot of resistance of pushback from the scientific community, because they think, well, they look down on social sciences. But some ecologists think that it's very, very important, because it's not, forests are not alone in the world. So humans live from forests. Some humans make a living out of gathering mushrooms, others from gathering wood, others, so I think it's a very old-fashioned way of thinking that imposes itself for us to think that physicists just do physics and biologists just have to do biology and so on.
Yeah, I agree that, let's say, on the one hand, there's a need for interdisciplinarity, and on the other, there's a push against it by individuals and also by organizations, in the sense that the way like universities, including ours, are structured, and the way funding agencies are structured inhibits interdisciplinary research and collaboration. So yeah, that's problematic.
And I think these concepts arise from considering more factors, no? From looking at the complexity of phenomena.
Yeah. And anyone else would like to suggest why we are still stuck with reductionist ideals?
I don't know. I would like to say that maybe it is because complexity is hard, in the sense that just you and me the other day couldn't agree, but we were talking about in terms of a simple topic. And when I have tried to talk to people in other disciplines, it has taken me a lot of time to just get to a base ground where we share the same language to start working on it. So I think it needs a lot of like cooperation between the people involved, and that's not easy. I don't know. That's my perspective.
Yeah, I guess it's also related simply to resistance to change by many people. If they, well, I had this several years ago. Well, it was before the pandemic. It was an event in the Prepa 6 with teachers from the high school, and they were telling me that, let's say, there was like a push to use like new tools for teaching. I forget what was I speaking about. Yeah, about complexity in education. So, I mean, we have the technology to give personalized education to students at different levels. And they were like, well, if some of our teachers still don't feel comfortable with a PowerPoint, then let's say it will be difficult to speak about, I don't know, inverted classrooms where students watch videos at home with the courses and then they go to class and have discussions because the teachers kind of have been 20, 30 years giving their class in such a way and they don't want to change that. So I've seen this also with colleagues from the social sciences, that now you have the tools to make harder social science in the sense that there is data to contrast social theories, but then you need to learn new methods for that. And of course it's difficult, but many people prefer just to continue doing what they have been doing already for decades than to learn new tools. And the problem is not only that, let's say, they continue and then they die and then the new ones will pick up the new ones, but they teach these old tools. So then the new generations, by the time they gain their independence, they will already be comfortable using those old tools. So it will be difficult for them as well to change. And well, also what we mentioned, that it was only with personal computers that it became possible to study massively complex systems. That was only in the 1980s. But if, to be honest, most computers until recently were very difficult to program. So that was also a big limitation for using computational models and computational tools for studying different systems. And in Ashby's case, it was with mathematics, but mathematics are also limited in the sense of how many variables you can consider. So I don't think it's so much that sociologists are like, oh, I don't like mathematics, or I'm scared by them, or I know some historians that confess, well, I studied history because I hated math. And then I thought, well, where can I go that I won't require mathematics? And then all surprised, they realize that they need to learn statistics on their own and, let's say, other things that are necessary to make sound claims about history. But anyway, it's not only that. I mean, the mathematics that were available until recently were simply insufficient to describe societies for many social systems. So there were people who had the mathematical formation, and you can see it in economy. Many people with a strong mathematical background. That doesn't mean their models are good, because simply the mathematics they use are limited. I mean, economy is much more complex than those models. So you could say that they don't fulfill the Ashby's law of requisite variety. So then they're not very useful. Yeah. And it's also that nobody has, I mean, it's not the case that this has been completely forgotten and nobody's using this. Many people do use these ideas, even with different names and with different approaches. But yes, it's slow. It is very slow. I think it's progressing slow. Yeah, maybe another 75 years and we'll be in a better position.
Maybe it also changed when people realize that it's given new solutions to old problems, and that these solutions are being better. I don't know. Maybe they will be incentivized to try this new approach.
Yes. At the end, it's a matter of pragmatic. If these new tools cannot solve new problems, then we will keep on using the old tools that were as bad as the new ones. So if we come up with tools that are better and can solve problems that the old tools were unable to solve, then they will start being adopted eventually. And I mean, they have been adopted. I mean, computational modeling is becoming standard in many disciplines. But yeah, the idea of, let's say, underlying adaptive computing, that is still something that is not broadly absorbed, because I mean, in many cases, to have the simplification of stationary domains, basically that that your variables don't change while you're analyzing, it allows you to study a problem analytically. If you have no stationarity, you can't do much analytically. And for some, that is a big drawback. But it's like, okay, do you want a poor model that you can study completely, or you want a good model that you cannot, let's say, explore exhaustively, or that you cannot make formal proofs about it? It's difficult to say which one is better, because they both have advantages and disadvantages. So I guess that time will tell. I mean, most probably they will continue coexisting as they have been for several decades. But I think it's useful to have a clear idea of, say, what's the role of each type of modeling approach. Let's say classical computing, adaptive computing. Yes, Amaury?
Yes, Professor. As I understand, we have to elaborate a report as a part of our final project. So my question is about the structure that we should follow to write this report. I mean, maybe we can follow the structure of a paper with an abstract, an introduction, methodology, results, discussion, etc. But I ask just in case.
Yes, that's precisely the idea. The structure of a conference or a journal paper, but then the length should be between 2,000 and 4,000 words, so not too long.
Okay, so the maxima is for 4,000 words, right?
Yeah, that would be about eight pages without figures.
Exactly. Right. Thanks.
So yeah, you can have abstract, introduction, related work, then method or models or proposal, results, discussion, feature work, conclusions, bibliography, references. I mean, it's not a strict structure because sometimes it's better just to start with the results and then you explain what you did. And sometimes it's better to kind of start building the suspense. No, actually, in scientific documents, it's not such a good idea to try to build up the suspense because very few people will actually reach the end of the paper. So it's better to put everything in the abstract, of course. But then in the introduction, to repeat again what will you do in the paper and what will be your contributions. So, to prepare the reader, okay, this is what I will find. And then as you read, you are finding all these things that you already know you will find in such an order. So yeah, no suspense. It's better because most people will not read your work. That's a fact. And from the few people that will read it, most will read only the abstract. And if they read a bit more, it's probably only the introduction and conclusions. So many people advise to include the relevant takeaways, first in the title, but then also in the abstract, but then to repeat those main takeaways in the introduction and conclusions. And then also that might motivate people to be curious and then say, oh, how did they reach this conclusion, and then go through the paper. Okay. Are there any more comments or questions? Okay. So, yes, Elio.
Okay, yeah, my proposal is to already the last semester, I took complex systems with Viviana Obregon and with Liz Mateos, and we made a draft to study the evolution, the time evolution of the visuality network of the annual hurricane energy. And that is my proposal to do with you to have what do you think about the work? And after that, to try to publish the work.
Yeah. Could you please remind me, how do you construct a network out of hurricanes?
Yeah, we use the algorithm that is called a visibility network, that consists that you establish the link for each dot in the time series, like if was a mountain or a landscape profile, and where each point is connected with the other points that you can connect with a straight line without to be interrupted by the landscape or by the profile.
But then it's not the dots in the time series, but dots in the cartographical map?
No, it's not a cartographical map. It's you translate the time series into a network, in a complex network.
But then which time series?
And in this case, is the time series of the total the tropical cyclonic energy in the world for each year.
So basically, in times when there's lots of cyclones, it goes up, and when there are a few cyclones, it goes down.
Basically, yeah, the total energy is directly related with the abundance and intensity of the tropical or all tropical cyclones around the world.
Yeah. But but then which are your nodes? The days?
Sorry?
What's the time scale of this time series? Like daily or hourly or?
It is the total annual for organic energy. You add the each 4 hours is measured the maximum velocity inside each hurricane, and then you square that value, and then you sum all the measurements for all the hurricanes in all the world, and then you have a number, and that is the total annual hurricane energy.
Yeah, but then you look at these 4-hour intervals for the time series, or just year by year?
Use it with satellites,
yeah.
Each 4 hours. Yeah.
But then in the network, which ones are the nodes?
The nodes, the
nodes. Yeah, the nodes and edges.
The nodes is the value of the energy. The nodes is each gear.
So each year is a different node?
Exactly. And the link is if you can see other year in the time series like it was a landscape profile.
Yeah. So basically from higher years, you can link to other years.
Yeah, to the
low year.
Yeah. From the higher, you can see the valleys, but dots in one valley cannot see.
Yeah. But it's I mean
the dots in the other valley. Click.
Yeah, it's symmetric, right? I mean, if you can see from one point another point, then it's vice versa, right?
Exactly. The links are symmetric. Come and go for the same. Each one see each other.
Yeah.
Yeah, are not directional network. And what I do is I build the complex network for the first 2 years, then for the first 3 years, then for the 4 years, and go on. And I plot the density degree of each year. And what I saw is the time evolution of the complex network.
Yeah.
What I studied in the paper is the time evolution of the complex network, the visibility complex network.
Okay. And then do you have already like some results? Like what's the distribution of the in degree of
everything is done. But Viviana considered that is lacking, is incomplete. Also, Gerardo Garcia Naumi consider that the work is incomplete. That I am using a technique, but I am not solving any problem. Then the work is incomplete because it's not starting from build knowledge. It's starting just for practice.
Yep.
And then they say that is wrong. That's have no sense. I need to design a physical problem where that such tool is the proper one to solve the problem.
Yeah, but, maybe it's not that it doesn't have sense, but let's say in order for it to be useful, you need to be able to interpret the results meaningfully. So then the question is, what does it mean that the temporal evolution network has the properties it has, as opposed to not having that.
Yeah, sorry. Yeah, Enrique Ascara was checking the work, and he realized that this unuseful the use of the technique, because the basic property that is discovered is that the degree what detects is the size of the place. Yep.
The size of what, sorry?
The size of the valley, which longer are the minimums.
Yeah.
Yeah. Then is
I mean, if
the
you can just
increase of the abundance of that is the degree.
Yeah. If you can use
and
that,
you can use that. Yeah.
For forecasting hurricane intensity for several years ahead, that would be something interesting. So,
yeah, I don't know.
For example, how many years you have data for?
50 years, 70 years in total since 1950.
Yeah. And I suppose the activity has been increasing recently with global warming.
No, the activity is stationary. Have a constant mobile mean and a constant variative variance or mobile variance. Variation.
Yeah. But then, I mean, I suppose that there are no rhythms like there's like a 7-year cycle where it goes up and down, right? I suppose there isn't such a regularity. Or there is.
We haven't for this data do that, but for previous data for the Northwest Pacific, we make a Fourier transform analysis. In fact, it was a self-correlation analysis, and we found 33 years periodicity. It's not evidence, but the Fourier transform reveals. I confirm it, and the Fourier transform reveals that exists some periodicity, some significant periodicity.
Yeah, because if you could use this or other technique to say, okay, the hurricane activity in the next 3 years will be this and this with this probability, that would be useful. And you can test it because you could assume that you have data until, let's say, 2010, and then you make predictions for the years that you have data for, and then you compare your prediction with the real data.
Yeah, but it's impossible to make a prediction because it's quite near to the Horst exponent is quite near to 0.5. It's always between 0.3 and 0.7.
Yeah.
It's in the unpredictable zone.
Yeah.
Then in fact, we found that it was another result that Gerardo think that we need to work on that. We found, but no us. In fact, was found in general that only the North Pacific is persistent. All in the rest of the activity and the hurricane activity is random, is unpredictable, not random, unpredictable. Includes chaos, could be chaos, deterministic, not deterministic, and random.
Yeah. Yeah, I mean, but then at least this tells you the limits of predictability, saying that, well, okay, we made this analysis and we were able to show that you can't predict this because of this and this and this.
Yeah, Yeah, we have done for the world activity, but we have done for request specific, and we know that the hurricane activity is unpredictable. The world hurricane activity only for the North Indian is the only predictable. Is persistent in fact.
Okay.
Okay. Okay, then maybe you can have a look in the paper, in the draft, and to help us to be meaningful within the interpretation. If maybe if you not, maybe somebody that you know and help us visual network algorithm.
Sorry, you broke for a moment. Could you please repeat?
Yeah. I would like to you to help us to find the meaning of the results.
Yeah, it's something we can discuss.
Thank you.
So next week we'll see something about synchronization. And I hope you have a great weekend.
Thanks.
You too. Thank you.
Bye.
You.